Hello. This is a question related to SN1 reaction. In this problem, we should draw the three-dimensional picture of the substrate based on this given name, which is this one. Let me show you why. If we number this carbon-bearing chlorine as 1, this is 2, and this is 3. So this is 1 chloro, 3 ethyl, 1 methyl cyclohexane. And the important part of this nomenclature is related to configurations around two chiral centers, which are this one, carbon number 1, and carbon number 3. As you see, configuration around carbon number 1 is S. Let me show you why. To determine the configuration, we should assign the priorities. Here, chlorine gains number 1, followed by this carbon, and then this is number 3, and methyl gains number 4. Now, if we look at this molecule from front side, because from this side, the methyl is seen in the back. Now, if we go from 1 to 2, and from 2 to 3, and from 3 to 1, we see counterclockwise motion, which indicates that the configuration of this chiral center must be S. Let's determine the configuration of another chiral center, which is carbon number 3, this one. Here, this carbon gains number 1 because it's bonded to carbon-bearing chlorine, followed by this carbon, which is gaining the second priority, and ethyl, this carbon of ethyl gains the third priority, and hydrogen has the least priority. Now, if we look at this molecule from front side, hydrogen will be seen in the back. Let's say this is I. Now, if we go from 1 to 2, and from 2 to 3, and from 3 to 1, we have clockwise motion. So the configuration around carbon 3 is R. Now, we should predict the product of this reaction in which this substrate reacts with acetate. The mechanism of this reaction is SN1 reaction, substitution nucleophilic unimolecular reaction. Why? There are two main reasons for SN1 reaction here. One, the structure of this substrate is a tertiary alkyl halide. So this is a bulky carbon. This is a crowded carbon. So this tertiary alkyl halide cannot undergo SN2 reaction. And the other reason for SN1 reaction in this case is related to the type of nucleophile. Here we have acetate, which is relatively a weak nucleophile compared to, for example, OH minus. Why? Because here we have a resonance between negative charge and carbonyl group. So this resonance makes O minus weaker nucleophile than, for example, OH minus. So here we have two conditions, tertiary alkyl halide and also a weak nucleophile. That means this reaction must follow SN1 mechanism. Now let's work on the mechanism. In SN1 mechanism, in the first step, we have heterolytic cleavage of carbon-chlorine bond to make this carbocation, which is a tertiary carbocation, and also Cl minus has left as a leaving group. Here in the reactant, this carbon has tetrahedral geometry, and the hybrid orbitals used by carbon to make sigma bonds are sp3 orbitals, hybrid orbitals. However, in the carbocation, here the hybrid orbitals used by carbon to make sigma bonds are sp2 hybrid orbitals. So the geometry around this carbon plus is a planar structure. So this is a tertiary carbocation with planar geometry. What's the next step of SN1 mechanism? Once this carbocation is formed, it will be rapidly attacked by nucleophile. Here, for nucleophile, there are two options to attack on carbocation, which is electrophilic center. This nucleophile could either attack from the front side to form this product. In this case, when this oxygen is attached to the carbocation from the front side, in the product, methyl must go away. It must go in the back because here this carbon is tetrahedral. And the other possible attack is from the back side. Here, this acetate could attack from backside, and now in the product, oxygen of acetate is attacked to this carbon, and this carbon-oxygen bond is in the back. And when we have attachment of oxygen from the backside, this methyl in the product must come forward in order for this carbon to have tetrahedral geometry. Now let's consider the relationship between these two products. As you see here, the carbon number 3 is not affected during the reaction. So the configuration around carbon number 3 remains the same for both products. However, for carbon number 1, here we have two different configurations. Here we have 1s, and here we have 1r. So what's the relationship between these two stereoisomers? Since only one configuration is reversed and the other configuration remains the same, so these two stereoisomers are definitely diastereomers. Let me show you, for example, how to determine the configuration around this carbon. Here, oxygen gains number 1, followed by this carbon, and then this is gaining number 3, and methyl gains number 4. Now, if we look at this molecule from this side, in which the hydrogen is seen in the back, now if we go from 1 to 2, and from 2 to 3, and from 3 to 1, we have counterclockwise motion. So here the configuration for carbon number 1 is 1s. Thank you very much for your attention.